In this video, we're going to look at a different method for solving second-order linear non-homogeneous ODEs. This method is called the method of undetermined coefficients. It's somewhat simpler than other methods such as variation of parameters. It requires some observation, and we need to make an educated guess for the form of the particular solution yp. It's applicable if r of x is of the form given over here. So we can have r of x being a constant, a polynomial of order n, exponential function, sine or cosine function, or the product thereof. And what we'll see is that, in fact, a lot of engineering and scientific applications, we see these non-homogeneous terms appear. So it's actually quite applicable. This is best demonstrated via an example. So let's consider the second-order non-homogeneous ODE over here. We see that r of x is equal to 8x squared. So it is a polynomial of degree 2. This ODE says that the second derivative of the function y plus twice the first derivative minus 4 times the function itself should equal 8x squared. As a first guess, let's try for the particular solution yp is equal to ax squared, where a is what we call the undetermined coefficient. So what we need to do, we just need to take the derivatives of yp and substitute them into the ODE. So the first derivative will be 2ax, and the second derivative, yp double prime, will just be 2a. Okay, so we substitute it into the ODE, and what do we get? So we have the second derivative, 2a, plus 2 times the first derivative, so that will be 4ax, minus 4 times the function itself, so minus 4ax squared, and that will be equal to our non-homogeneous term, 8x squared. And now it's just a matter of solving for our undetermined coefficient. So what we need to do is equate the coefficients of like terms. So all we see is on the left-hand side, we have an x squared term. On the right-hand side, we have an x squared term. So we can say that minus 4a is equal to 8. Okay, this seems fine so far. But we also have other terms here that we need to figure out. So we see that we have an x term on the left-hand side, but we don't have an x term on the right-hand side. So our equation would suggest that 4a is equal to 0. We also have a constant term here, but we do not have a constant term on the right-hand side. But this equation suggests that 2a should also be equal to 0. So if you're confused and you see that there are some contradictions, you're not alone. A cannot simultaneously be equal to 0 and minus 2. So therefore, our guess solution of ax squared is incorrect. So let's guess another solution. So let's assume, we'll call this guess 2. Let's assume that yp is a polynomial of degree 2. So we're going to add a few extra terms. So we have ax squared plus bx plus c. Okay. So compare it to our initial guess where we only had the first term, we're adding 2 extra terms here. Again, we will need the derivatives in order to substitute in our differential equation. So yp prime will be equal to 2ax plus b, and yp double prime will be equal to 2a. So now again, we substitute back into the original ODE. So we have the second derivative, 2a, plus 2 times the first derivative, so that will be plus 4ax plus 2b, minus 4 times the function itself, so minus 4ax squared minus 4bx minus 4c. And all of this will be equal to the right-hand side, given by the ODE as 8x squared. And again, we're going to equate like terms on the left and right-hand side. So again, we see that we have x squared and x squared. So we are going to say that minus 4a is equal to 8. So we've taken care of this term here. Now we can look at the x terms. So the x terms will tell us that we have 4a minus 4b, and that will be equal to 0 because we have no x's on the right-hand side. So we've taken care of 2 extra terms over here. And then finally, we have 2a plus 2b minus 4c, and that also will be equal to 0. So we have a system of 3 equations and 3 unknowns, the unknowns being a, b, and c. I will let you solve this on your own, but what you will find is that a equals b equals c and is equal to minus 2. And as opposed to our initial guess, we have no contradictory terms. So what this tells us is that we have reasonable undetermined coefficients a, b, and c that we can substitute in our guess for yp, and it is an appropriate particular solution for the given ODE. So the particular solution will be of the form minus 2ax squared minus 2x minus 2. And this is the answer that we seek. Before we continue with a few more examples, I want to point out a few important notes. The first one is what we call the superposition principle for particular solutions. And this helps us deal with non-homogeneous terms that might be complex. That is, of the form like this, where you have perhaps multiple terms. Okay? So what this says is that if yp1 is a particular solution of this non-homogeneous differential equation, and yp2 is a particular solution of this non-homogeneous equation, so where the right-hand sides are different, r1 and r2, then yp1 plus yp2, so the summation of the two, is a particular solution of this final ODE over here, where the right-hand side non-homogeneous term is the sum of these two non-homogeneous terms. And this could be extended to multiple terms, so we are not just restricted to 2 non-homogeneous terms. Another important note is the one that follows here, is that if a non-homogeneous term is a solution to a related homogeneous equation, then the assumed form of yp should be multiplied by the dependent variable. That is to say, if, for example, r of x is equal to, say, e to the 2x, as an example. But one of our fundamental solutions, let's say y, for our homogeneous equation, the related homogeneous equation for the ODE, if let's say one of the fundamental solutions is also e to the 2x, let's say, then we cannot propose that yp is equal to some undetermined coefficient multiplied by e to the 2x. And so what this is saying is that we must multiply this assumed form by the independent variable. That is, we should say that yp is equal to a multiplied by the independent variable multiplied by the assumed form e to the 2x. And we will look at some examples later. Before we wrap up, I'm including this useful table of particular solutions, yp, that can be used for a given r of x, a non-homogeneous term on the right-hand side. So if we encounter an r of x that is a simple form such as exponential form, then we can propose a particular solution of the form given here, p multiplied by e to the alpha x. But again, all of these proposed solutions, you need to keep in mind different things such as the principle of superposition, but also the important note that the proposed particular solution cannot be the same as one of the fundamental solutions to the homogeneous equation, as we just mentioned here above. If the right-hand side is a polynomial of order n, then you can propose a polynomial of order n as a proposed particular solution. If you have a cosine term or a sinusoidal term, then your proposed solution should be of this form given here, where you have the summation of both a cosine and a sine term. And the reason for this, as you know, is that as you take derivatives of a sinusoidal, of a sine term or a cosine term, it's alternating between sines and cosines. That is, the first derivative of a sine is a cosine, and then and then you take the subsequent derivative, and you're back to a sine. This case over here looks at the product of an exponential function multiplied by a polynomial of degree n. And what this is saying is that if you encounter this on as your non-homogeneous term, then your proposed solution should be of this form here, where you are multiplying the exponential function by a polynomial of degree n. Similarly, if you see any of these terms, so you have an exponential multiplied by a sine or an exponential multiplied by a cosine, or the summation thereof, then the right-hand side should be of this form here, where you have the exponential multiplied by the summation of a sine and a cosine with two undetermined coefficients. So this is a useful table to help us work through some non-homogeneous second-order ODEs.